Okay, this is a lesson on using maple to find maxima, minima, and inflection points. So this is what we want to be able to solve. Given a function f of x, find the intervals where the function is increasing and decreasing, and find the relative maxima and minima. Also, find the intervals where the function is concave up, concave up, and concave down, and find the inflection points. So this is a basic problem in calculus, and let me work on this with one of the problems from homework 6. So we have the function f of x is the cubic 2 times x cubed plus 7 times x squared minus x minus 4. And if we want to know what's going on, let's just plot f of x. Looks like that. It's not clear what's going on here, so maybe let's just plot it from -5 to 5. Okay. So this gives us a better picture of the function, maybe even -5 to 4. So like most cubic curves, it goes up, comes down, and goes up. So what is the derivative? The derivative of the function f at x is this quadratic. And you recall, or you learn in Math 175, that f of x is increasing where the derivative is greater than 0, and decreasing where the derivative is less than 0. So let's see if we can solve the inequality. When is the derivative of f of x greater than 0? Oops. Let's see. Let's try solve. Okay. So solve not only solves equations, but it can solve an inequality. And we have 2 intervals where this function is increasing, that is, where the derivative is positive, so the function is increasing. Solves finds it exactly, and if you convert this to decimals, EVALF, and percent means what we just calculated, from -infinity to -2.4, around there, the function is increasing. And from 0.69, it's right around here, the function is increasing. So let me just say, on these intervals, the function is increasing. And let's look and see where the derivative is negative. We get this interval. And if we convert it to a decimal, oops, we get this interval here. So the function is, so on this interval, the function is decreasing. And relative maxima and minima occur at critical points of the function. That is, points where the derivative is 0. So suppose we want to solve the equation these are the points where the derivative is 0. Let's actually use fsolve. So this point is a maximum. And this point is a minimum, which is exactly what you see when you look at the curve. And let's recall the second derivative test. If the derivative of f of x is 0, and the second derivative is positive, then x is a maximum, x is a minimum. If the first derivative is 0 and the second derivative is negative, then x is a maximum. So let's just check what we did by using the second derivative test. D at 2 of f of x, that's the second derivative. And let me give these 2 points a name. Let me call it, let's say, CP for critical points. So CP1 should be capitalized. CP1 is the first critical point. CP2 is the second critical point. So if I evaluate the second derivative at CP1, it's negative. Therefore, this second critical point is a relative maximum. Let me evaluate the second derivative at the second critical point. It's positive. So if the first derivative is 0 and the second derivative is positive, you have a relative minimum. So this is all consistent with what we can see at the picture and what we calculated. What about concavity? So let's solve the equation. When is the second derivative of f of x greater than 0? Minus 7/6 to infinity. Let's see. Did f solve to that? No. So let's convert that to a decimal. So on the whole interval, f of x is concave up on this interval because the second derivative is positive there. Here it is. From here on up is positive. Where is the second derivative negative? There. So f of x is concave down on this interval. When is the second derivative equal to 0? At this point. So this is the inflection point of the function. Okay, let's do one more example. Again, from the homework. This was in problem 1E. Suppose we take h to be the function x goes to 3 times x over 2 times 1 plus 4 times exp of minus x over 3. 3 halves x times 1 plus 4 e to the minus x over 3. What does this function look like? Let's plot it. That's interesting. Goes up, keeps going up. Okay. Where is it increasing? Where is it decreasing? So what is the derivative of the function? It's equal to that. So suppose we want to know where is the function increasing? That's where the derivative is greater than 0. Why does it say this? Maybe Maple can't do this. Let's plot the derivative. So looks like this function is always positive. Positive, 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 positive. So it's always increasing. But somehow Maple doesn't want to solve this inequality. It's fine where the derivative is 0. This means it can't solve it. Something's not right because Maple should be able to solve this inequality. We have this function. You plot it, it looks like this. It looks like it's always increasing, that the derivative should always be positive. And this is the derivative. So that's definitely correct. But it doesn't want to tell me when it's positive. I plot the derivative, it looks like this. This is clearly greater than 0. That's just this is what the function looks like. So this function is strictly increasing. Increasing for all x. Maybe that's what this means, but I don't know. But the derivative is always positive, so the function is increasing for all x. Therefore, f of x has no relative maxima or minima. What about concavity? If we take the second derivative, it's this straight line. So if we want to know where is this function greater than 0, from minus 7/6 to infinity. So minus 7/6 is right about there. Oh, I'm sorry, it should be h. That is the second derivative. And this is f of x concave up in this interval. That is, from 6 to infinity, it's concave up. When is it less than 0? From minus infinity to 6. So it's concave down on this interval. When is the second derivative equal to 0? That's 6. So x equal 6 is a point of inflection, because at x equals 6, the curve changes from concave down to concave up. Okay. That is the story.